If you've ever worked with a database, you know that feeling, that sinking feeling in your stomach when a query just grinds to a halt. Well, today, we're going to talk about the unsung hero of database performance, the SQL index. We're going to flip the script and turn that query killer into your application's absolute performance hero.
So picture this. It's peak traffic hour, the app is slowing down, users are starting to complain, and your monitoring dashboard is lighting up like a Christmas tree. You're scrambling, looking for a bug in the code, but the real villain isn't in your application logic. Nope. It's something silent, something hidden, lurking deep inside your database.
It's the question that keeps developers up at night, right? You've got a table with millions, maybe tens of millions of rows, and a simple select query that used to be instant now takes forever to run. And let's be real, this isn't just some minor inconvenience. This is a full-blown scalability crisis just waiting to happen.
So what's actually going on under the hood that's causing this crippling slowdown? Well, before we can find the solution, we have to really understand the problem. And the problem, it turns out, is a single, incredibly resource-hungry operation that we have to stop at all costs. It's called a full table scan. This is the database's brute force approach. When your query doesn't have a better plan, the database has no choice but to literally read every single row, one by one. It's like trying to find a single word in a 1,000-page book by reading it from cover to cover. On a tiny table, no big deal. But on a production table with millions of rows, it's a complete disaster. And this is where the magic really comes in. A full table scan, that's what we call an O of N operation. The time it takes grows in a straight line with the number of rows. More rows, more time. Simple. But an index seek? Oh, that's O of log n. Now what does that actually mean? It means your table can grow from 1 million rows to 1 billion rows, and the time it takes to find a record barely even budges. It's the difference between something being slow and something being practically instantaneous. So how do we get that incredible O of log n performance? How do we unlock that speed? We use the database's not-so-secret weapon, the index. This is the tool that transforms those slow, lumbering queries into lightning-fast surgical strikes. So what is an index, really? At its core, it's just a separate data structure. You can think of it like a special lookup table. It's a highly optimized, sorted copy of just the columns you want to search on. So instead of scanning the whole giant table, the database just scans this much smaller and more efficient index. And the secret sauce behind its speed is usually a data structure called a B tree. So how does this B tree thing work? Well, it's actually way more intuitive than it sounds. The database starts at the top, at the root of the tree. With every single comparison it makes, it gets to eliminate huge chunks of the tree, allowing it to navigate down the branches incredibly quickly until it lands on what's called a leaf node. And that leaf node has exactly what it needs, a pointer, an address, that points directly to where the full data row is stored on disk. It's a precision strike, not a carpet bomb. Okay, but here's the thing. Not all indexes are created equal. The term index is just the beginning. Your database actually gives you a whole toolbox of different index types, and each one is designed for a very specific job. So let's open up that toolbox and see what we've got to work with. The first big distinction you need to know is between clustered and non-clustered indexes. A clustered index is really special. It actually defines the physical order the data is stored in on the disk. And since you can only sort the data one way, you can only have one clustered index per table. Think of it like the main table of contents in a book. A non-clustered index, on the other hand, is a completely separate structure. It's more like the topic index you find at the back of the book, a separate list of pointers. And just like a book can have multiple indexes, a table can have many non-clustered indexes. Now listen up, because this next part is where so many developers get tripped up. When you create an index on multiple columns, called a composite index, the order of those columns is everything. It's a rule called the leftmost prefix rule. So if you have an index on, say, last name, then first name, the database can use it to efficiently look up people by their last name, or by their last name and first name. But, and this is the key part, it can't really use that index to find everyone whose first name is John. Just like a phone book, you have to start from the left. This quote, "This is the dream. This is the holy grail of index tuning." I mean, what if your query was so efficient that it didn't even have to bother reading the main table at all? Well, that powerful idea leads us to our next tool. And that dream has a name. It's called a covering index. It's basically a composite index that includes all of the columns your query needs to return. So if you're selecting, say, a customer ID and an order date, and your index contains both of those columns, the database can answer the entire query using only the index. It never has to do that second hop to the main table, which makes it unbelievably fast. Okay, but what if you're only ever querying a really small slice of your data? I mean, indexing a table with millions of rows just to find a few thousand active records, it feels kind of wasteful, right? Well, for that exact scenario, we have a true secret weapon. So check this out. This is the perfect use case. Imagine you have an orders table. 95% of the orders are closed and only a tiny 5% are still open. But your application's dashboard is constantly querying for just those few open orders. A regular index would have to cover all the millions of closed orders too, which is just not efficient at all. This is where the filtered index comes in and just saves the day. It's basically a non-clustered index that has a where clause built right into its definition. So in our example, we could create an index where status equals open. And the result? A tiny, hyper-efficient index that only contains that 5% of the rows you actually care about. It saves a ton of disk space and makes those specific queries fly. And look, this isn't just some textbook theory. This is a real story from the trenches. By adding a single, well-placed filtered index, a client's reports went from taking several minutes to running in just a few seconds. And the index itself? It shrank from a massive 30 gigabytes all the way down to just 2. The impact can be absolutely phenomenal. So, indexes are amazing. We should just put them on everything, right? Solves all our problems. Whoa, not so fast. Because using them the wrong way can actually make your performance worse. So let's talk about the common traps you really need to watch out for. Okay, this is probably the single most important concept to understand about indexing. It's a fundamental trade-off. Yes, indexes make your select queries way faster, but there's no free lunch. Every time you insert, update, or delete a row, the database has to do extra work to update every single index that row is a part of. So the more indexes you have, the slower your writes become. And that trade-off leads us directly to these huge mistakes we see all the time. The biggest one? Over-indexing. Just creating an index for every column just in case. You will absolutely kill your write performance. Another classic is indexing a column with low cardinality, like a gender column with only a few unique values. The index just isn't selective enough to help the database. But honestly, the worst mistake of all is just winging it. It's just guessing. So, how do we stop guessing and start knowing? How do we level up and become true optimization pros? It all boils down to one simple, powerful principle. You have to measure, don't guess. Every major database gives you a command, usually called explain or explain analyze. When you run this on your query, the database gives you back its execution plan, the exact step-by-step recipe it's going to use. It'll tell you plain as day if it's using one of your shiny new indexes or if it's falling back to that dreaded full table scan. This tool is your ground truth. I love this quote because it sums everything up perfectly. You can't just blindly add indexes. Effective indexing is an art of balance. You need just enough to make your critical reads fast, but not so many that you grind your writes to a halt. It really is a thin line, and the only way to walk it is to measure the impact of every single change you make. And that brings us to the biggest takeaway of all. I want you to stop thinking of indexes as just a simple performance tweak. They're a fundamental part of your application's architecture. A smart, deliberate indexing strategy is what allows your database to scale from thousands of rows to billions without falling over. It's not just about making one query faster today, it's about building a system that can handle the growth of tomorrow.